how to draw triglycerides, which is a subgroup of lipids. So here we see a basic cartoon that shows us a triglyceride. So we see the glycerol molecule that makes up the backbone that holds the 3 fatty acid tails together. But today we're going to go past this basic shape, which if you notice looks a bit like an uppercase E. And we're going to learn how to draw this on a molecular level, but we're also going to make some connections with some background information as to why we care. So lipids, they are a diverse group of organic compounds, and lipids have a subgroup of triglycerides that we're going to focus on today. Now, this organic compound means that it has a carbon skeleton, and we notice that this is insoluble in water, unlike other molecules we've studied thus far. If you take glucose and you put it with water, it will dissolve. Well, glucose is polar. If you take salt and you put it with water, it will dissolve. Well, that's because it's ionic. But lipids, including fats and oils, will dissolve not in water, but it will dissolve in nonpolar solvents instead. So today we're going to be focused again on the triglycerides, which are fats and oils. Later in class, we will discuss phospholipids and steroids. So fats store large amounts of energy, actually 2 times more energy than carbohydrates, and we'll come back to that shortly. And they are made of a glycerol backbone, 3 fatty acid tails, and they have ester linkages that hold the fatty acid tails to the glycerol molecule. So what are the key functions of fats? Well, they store energy. For example, 1 gram of a fat will have about 9 calories of energy stored in its bonds, whereas 1 gram of carbohydrate would have approximately 4 calories of energy stored in its bond. So twice the energy for the same amount of mass. So more energy, less weight than other molecules, which makes them highly energy efficient storage molecules, whether it's storing for a famine in an animal or whether it is storing energy in oils inside seeds and nuts so that the next generation of plants can grow out. So another key function of fats is that they can cushion vital organs. For example, you have a little bit of fat around your kidney area to help cushion your kidneys. Your kidneys are located on the back side of your body on opposite sides of your spinal cord. And they are a little bit vulnerable to the outside world, but by having a fat layer with them, it helps provide a little bit of a cushion. Then we have insulation. You have what we call subcutaneous fat, which is the thin fat layer right below your skin that acts like an insulating blanket for your body. Now let's focus on the key focus for this video, which is how we draw a triglyceride, or a fat or an oil. Now, to make this easy to draw, I'm going to have to exaggerate the covalent bond length between the 3 carbons that make up the carbon skeleton of the glycerol molecule. So the glycerol molecule has 3 carbons, and then we add in our hydrogens. And then we're not going to draw the whole glycerol molecule. We're only going to draw the component of the glycerol molecule that is then bonded on to the fatty acid tails. You can draw glycerol separately, but these H's would have an hydrogen, or these oxygens would have a hydrogen attached, making a hydroxyl group if we were to draw the glycerol independently. So this is glycerol. And let's highlight that to illustrate. So this is our glycerol component of our triglyceride. And then it bonds onto the carbon that makes up the first part of the fatty acid tail, and that carbon has a double bond up to an oxygen. And then we're going to try and represent the angles of carbon when it bonds, because carbon has the tetrahedral bonding angles. So we're going to use a bit of a zigzag here. So up a little, down a little, up a little, down a little, as we draw our fatty acid tail. Now, fatty acid tails can vary in length. So this one that I drew has 1, 2, 3, 4, 5, 6, 7, 8, 9 carbons, though that's really short for most fatty acid tails that you would find in nature. But screen length does dictate how many carbons I can realistically draw on there without it getting too messy. And then this is going to be a saturated fat, which means that every carbon is going to be holding onto the maximum number of hydrogens, and no carbons have double bonds. So all the interior carbons have 2 hydrogens, and the last carbon would have 1, 2, 3 hydrogens. So 1, 2, 3, 4 bonds for that carbon. Okay, so that is our next So here we have our top fatty acid tail. Now let's draw the middle fatty acid tail. Again, we start with the carbon and the double bond to the oxygen, and then up, down, up, down. I'm going to make a really short one here. 5 long, 5 carbons. 1, 2, 3, 4, 5, 6 carbons long. And then we add in our hydrogens. Again, we're making a completely saturated fat, something that would tend to be solid at room temperature, probably be found in an animal. And again, the end carbon needs 3 hydrogens. And let's just circle it. So here we can see this is fatty acid tail number 2. And then our third, because tri means 3, has 3 fatty acid tails. And 1, 2, 3, 4, 5, 6, 7. Hydrogen, hydrogen, hydrogen. Many, many hydrogens. Again, another saturated fatty acid tail to make up our end product of a saturated triglyceride. And let's circle that last. Triglyceride. So 1, 2, 3 fatty acid tails. Oh, look, that's an easy way to remember fatty acid tails are a key component in triglycerides because triglycerides are a type of fat and fatty acids tails, F-A-T. So here we can see actually how that molecule formed. We can see that the fatty acid tail was once separate from the glycerol, and through a process we call dehydration synthesis, which we will study much later, we can see how a hydrogen from the glycerol and an OH from the other molecule came together to form water, so dehydrated the 2 molecules. And then the end result when you do that 3 times is that you get a triglyceride molecule, and the bond between the fatty acid tails and the glycerol molecule is called an ester linkage. And you can see that each triglyceride actually has a very unique type of name based on the fatty acid tail composition, but that goes beyond the scope of this course. So let's just wrap up with a few final details about fats and oils and lipids altogether. So again, to review, they are not soluble in water. But the fatty acid tails that we find as the key component in the E shape of the triglyceride, these right here, they can all have the same length fatty acid tail, or they could have different lengths. Okay? And they can vary in length. We can also have double bonds, though double bonds makes it not a saturated fatty acid tail, but an unsaturated fatty acid tail. And that leads for more variety options because how many double bonds? 1 double bond, 2 double bonds, 3 double bonds. And where are those double bonds located? Between carbon 2 and carbon 3, between carbon 3 and carbon 4, etc., etc., etc. So much variety. And so speaking of these saturated and unsaturated fats and oils, let's just do a quick review. So a saturated fat or oil would have no double bonds. It carries the maximum number of hydrogens, and every carbon would have a single bond in the fatty acid tail makeup. So maximum number of hydrogens. And this tends to be solid at room temperature. On the next slide, I have a visual that helps you understand how that is possible. And these are usually animal fats. And examples would be bacon grease, lard, and butter. Unsaturated fats and oils, there tend to be 1 or more double bonds present. And that leads to these kinks, these little bends, and that makes it really difficult for the molecules to pack together, and therefore they tend not to solidify. And so therefore they tend to be liquid at room temperature. These are most commonly found in plants instead of animals, and some examples you might have come across: corn oil, olive oil, and peanut oil. So finally, let's just explore the slight differences. So here we have lard, and I will highlight for you that right there is the glycerol backbone. Right here on another molecule, glycerol backbone. Now let's move to a highlighter. Here's one fatty acid tail, another fatty acid tail. You can see how it's using that zigzag to much better represent what happens with carbon and its tetrahedral bonding angles. And so here the next molecule over, another fatty acid tail, another fatty acid tail, another fatty acid tail. So the zigzags tend to complement each other and allow within a molecule it to form a nice tight structure. And then it can form a nice tight structure with the molecule next to it. And so therefore, saturated fats and oils tend to be solid at room temperature. On the other hand, here we have olive oil. So there's its glycerol backbone. Here's another molecule's glycerol backbone. Now let's follow the fatty acid tails. Fatty acid tail, single, single, single bonds. Oh, double bond causes a bend. Single, 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 single bond, double bond causes a bend. Double bond causes another bend. Wow, that turned a corner. Here's the third fatty acid tail. Single bonds, double bond bend, double bond bend, double bond bend. Oh my! So if we do that again on the next molecule next to it, bend, 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 bend. You can see how it's practically impossible for one olive oil molecule and another olive oil molecule to neatly stack together. And if they cannot neatly stack together, they're going to slip past each other easily. And so therefore, most oils tend to be liquid at room temperature,